Hello everybody, welcome to our video solution to problem 10 from Superquiz 2. This was one of the optional problems from the exam. And in this problem, we're trying to prove a very useful formula about the cardinality of the union of two sets. We actually saw this in Superquiz 1 as one of the problems, so here we're actually proving the formula. So the formula says if you're trying to compute the cardinality of a union of two sets A and B, you can compute it by adding up the cardinalities of the individual sets, A and B, and then subtracting the cardinality of the intersection. So let's see why this is true. Well, let's start by looking at the level of sets. Let's forget about cardinalities for a moment. If I have a set A and I take some element, let's call it X in A, then there's two cases. Case one is that X is also an element of B. And if it's in B, that would mean that X is in the intersection of A and B. Case 2, X is not in B, right? Equally likely, I guess. In which case, we would say X is an element of the set A, but it is not an element of the set B. Okay, so this little backslash symbol is often used for set minus, right? Meaning you take all the elements in A that are not in B. Okay, it's also sometimes written as A minus B. So in either case, this means the set of all A and A such that A is not an element of B. All right, so every element in A satisfies one of these two cases. It's either in B or it's not in B. And this tells you, thus, A is equal to the union of all the elements in case 1 and case 2. So actually, let me write case 2 here first. So it's in either A but not in B, or, and I'm going to write a union, but I'm going to put a dot in here, and that dot means disjoint union. Okay, meaning that there's no element that's going to be in both pieces. So it's either in A and not in B, or it's in both, in which case it's in the intersection, A with B. Okay, so we now have a way of breaking up any set with respect to another set. You can write it as a disjoint union of the elements in A not in B with the elements that are in A and in B, right? That they're in the intersection. Okay, now the beauty of a disjoint union, right? From a pictorial point of view, disjoint unions look like that. All right, this is what a disjoint union looks like. All right, you have two sets and you get everything in both, and there's nothing which is in the intersection. And it's very easy to compute the cardinality of a disjoint union. You simply add the size of the two sets. So if I had here some set C and some set D, the cardinality of this disjoint union is just going to be the sum of the cardinalities of the individual sets. Okay. Okay, cool. So that means we actually have that the cardinality of A is the cardinality of A without B plus the cardinality of A intersect B. So for similar reasons, the cardinality of B is going to be the cardinality of B without A plus the cardinality, again, of the intersection of A and B. Now, once we have this, we can, well, let's go back up a second. Whoops, go back up here. We have now a cardinality of A and a cardinality of B, and that's what this formula, right, has on one side of it. So let's write that down. Cardinality of A plus the cardinality of B. Of course, we want to subtract the cardinality of the intersection. And what does this equal? Well, we have four pieces, two of which are the same. So I have the cardinality of A without B. I have the cardinality of B without A. I have two copies of the cardinality of the intersection. And then I'm subtracting at the end a copy of the cardinality of the intersection. Okay, and so this piece here just becomes one copy of the cardinality of the intersection. So you have A intersect B. Okay, now what was the other side of this supposed equality? We needed the cardinality of the union. So we're looking for the cardinality of the union. Well, let's write down what the union looks like. So the union of A and B. Well, what does it mean to be in A and B? So if I have some X, which is in A union B, this implies that X, well, it could be in A or it could be in B. If it's in A, it might also still in B though, right? This is not an exclusive or. Okay, so this is equivalent to saying that, well, let's see, it could be in A but not in B, right? So it might be in there. Or it could be in A and in B, in which case it would be in the intersection. Or, well, let's see, if we know it's in B, and if it's also in A, well, then it's already in the intersection. So we've already handled that. Or it might not be in A, in which case it'll be in B, not A. So this tells us that being in A union B means you're in one of those sets. So A union B is equal to the union, and now it's a disjoint union because you can't be in any three of these at the same time. Right? It's either going to be in A but not in B, or, we'll just write this first now, B and not in A, exclusive or, right? These are exclusive ors, or it's in A intersect B. Okay, so we'll put some parentheses to make it obvious what we're talking about. Okay, so A union B consists of elements which are in A but not in B, or B and not in A, or in both. And again, because this is a disjoint union, it's very easy to write down the size of the union. It'll be the size of A but not B, plus the size of B but not A, plus the size of the intersection. And that's exactly what we had up above. Size of A not B plus the size of B not A plus the size of the intersection. And therefore we conclude that the size of these two sets is exactly the same.